Now, frequently when we're talking about materials and things we've talked about so far, there are measurements we can take of them. We can say, well, we have, a mass of 37 grams of something, or we can say, we have a volume of whatever. When we start talking about things like gases, it's really difficult to think of them in terms of that because we don't want to count up the number of molecules, okay? Because there's just too much. There's just a ridiculously large number of molecules in the air that's floating around. And at the same time, we can't just put a scale and weigh it. Now, it does have some mass, but the fact of the matter is it's so sparsely scattered throughout the room that it'd be very hard for us to measure it. And we don't want to talk about, the amount of number of particles because there's a huge number. We have something called Avogadro's number, and we talk about moles of gas. Avogadro's number says 6.02 times 10 to the 23rd particles in 1 mole. So we can talk in terms of moles. That's a quantity of gas. We say, well, we have 5 moles of this. Well, if we say we have 5 moles, you say, well, if you want to know how many you have, you would take the 5 moles, multiply times Avogadro's number, because that is particles per mole, and that would tell you how many particles you had. And I say specifically particles rather than saying atoms, because frequently in gases, we can have gases that are made up of molecules, not just atoms. Right? Carbon dioxide, that is a single molecule, so it could be molecules per mole if you're talking about carbon dioxide. Or if you're talking about something that's a diatomic gas, it floats around as H2. There's 2 hydrogens that are tied together. Well, if that's the case, then it would be molecules per mole, whereas we could be talking about something, the number of atoms per mole as well. But we just take, the number of moles times the Avogadro's number will tell us how many particles there are, if we care to know how many particles there are. But more commonly, we want to talk in terms of moles when we're talking about gases. And we can also use this idea of number of moles when we're talking about atoms, things on that scale, or molecules of gas floating around. The mass is so small that it doesn't make sense to all the time. And what we just saw, 6.02 times 10 to the 23rd. That means that the mass of something like that would be on that kind of order, negative 23 type magnitude. So very, very, very small masses. So it makes more sense to talk of these things in terms of what are called atomic mass units. And basically an atomic mass unit, commonly referred to as an AMU, is just we look at something like hydrogen, and we say, hydrogen, what does it have? It has 1 proton and 0 neutrons. That's the primary mass in there. There is an electron floating around, but it weighs 1/1000th what the proton is, so we don't worry about it. So we say hydrogen has 1 atomic mass unit. And we say, well, what about, let's say, oxygen? Well, oxygen has 8 protons and 8 neutrons, and hence it has 16 atomic mass units, and so on and so forth. We can go throughout the periodic table, and each element that we come across, we can figure out how many protons, how many neutrons, fairly easily based on the proton number, and which is also known as Z in the periodic table. And there'll be an atomic mass number, and from those we can figure out what the how many atomic mass units this has. Now, what this really tells us is, for instance, this is obviously oxygen is roughly 16 times as massive as a hydrogen atom. Okay, but again, we're talking about masses that are so small that it doesn't matter a whole lot. We can't really make that kind of measurement. But what we can also do is we can determine based on this, like how much does an atom of oxygen weigh? How much does an atom of hydrogen weigh? And the way that we do that is really what this is. This is the mass. This is the mass per mole. Okay, so for instance, I would say this is 1 gram per mole. Okay, there's 1 gram per mole, and we know that there's 6.02 times 10 to the 23rd atoms per mole. And if I want to figure out what the basically the mass of a hydrogen atom is, I look at this and I say, well, here I have units of grams per mole, here I have units of atoms per mole. If I want to figure out how many grams it is for one atom, I would do this operation. Grams per mole divided by atoms per mole. And remember how to divide fractions. You would flip the second one and multiply, and when you would do that, the moles would cancel out and you would end up with the number of grams per atoms. So I take that, 1 over 6.02 times 10 to the 23rd, and the units that I'm going to get are going to be, that's going to be the amount of grams in one atom. And that number, I didn't do it already, but gives me 1.66 times 10 to the minus 1.66 times 10 to the minus 24 grams in one atom. If you were in kilograms, you'd say 1.66 times 10 to the minus 27 grams in one atom. And in contrast, if we were talking about oxygen, it has 16 AMUs. The entire process would be the same, except I have a 16 here, so it'd be 16 times as big. And I was talking about uranium-235, it has 235 atomic mass units. It'd be a 235 on top of there instead, and so it'd be 235 times as big.